So if we are presented with a generic equation that reactant A plus reactant B yields a product, should we use reactant A or reactant B for our calculations? And really it's going to come down to which one limits the reaction. The one that limits is going to be the one that we'll want to use for any and all calculations associated with this reaction. Right? So we can say, all right, well, first what we need to do is calculate the number of moles of reactant A and reactant B. We've done that before. And from that information, we will then divide by the respective coefficient for that reactant. So if this is the actual reaction process, just reactant A plus reactant B yields product 1, then if this is balanced already, we would divide the moles of reactant A by 1 and see what the result is, divide reactant B by 1 and see the result, and then we would then compare them. The reactant having the smaller result is the limiting reactant. The one which has its coefficient go in fewer times will be the limiting reactant. And then from that point on, you'll be using that limiting reactant amount for any and all calculations for stoichiometry. Right? Because once that reactant is used up, you can't make any more of anything else, nor would you use any more of anything else. All right, so simple enough. So if we use the aluminum chloride making aluminum chloride from previous, right? If we consider, remember we mentioned that we're going to consider we had 125 grams of each. And we talked about like which one would actually limit the reaction. I think we said the chlorine gas would run out first. Well, we first would want to convert both of these to moles, right? So we have 4.63 moles of aluminum, right? That's what we have to work with. Right? We compare that to what do we have as far as chlorine gas. Right, 125 grams divided by 71 grams per mole. So we have 1.76 moles of chlorine gas. Just because we have more moles of aluminum and fewer moles of chlorine does not always mean that the chlorine is the limiting reactant. We have to go to the balanced chemical equation to see at what ratio are they being used. Because if we're using aluminum 5 parts to 3 or something, then we may run out of aluminum first, because we'll be using a little bit more each time through the process than we would of the chlorine. But we have a 2 to 3 ratio, so we're going to we complete step 1 here. We're now going to divide by the respective coefficients, right? And that gives us a couple values to compare. There's really nothing we can do with these values as far as like the amount of something being made or used, but it will at least give us a ratio of how much per time through the equation they are used relative to each other. And that which comes out the smallest is the one that is limited. Right? So that means that is the limiting reactant. We should have leftover aluminum after this process. Right? But we start every calculation now from what we actually have. All right, so in this example then, determine which is the limiting reactant, iron or chlorine. So we did that. Remember, this is a volume of gas, so we would use molar volume to convert to moles. Okay, so we're going to divide each by the coefficient, and yeah, we find out that iron actually comes out slightly less, so iron would be the limiting reactant. Okay, so then how many grams of iron chloride are produced? We know that we have 4 moles of iron. So we can start with the mass, or we can go right to, since we already calculated this, why do that all over again? Right? We already know the number of moles of iron. So you're going to get the same answer. You will get the same answer. I'm just saying that if you're in a time crunch, you've already calculated this to determine the limiting reactant anyway, so you might as well use that. All right, so this is kind of including this first step here, where we divide by 55 grams the molar mass of iron. Okay, so now we're in moles of iron. We convert from moles of iron to moles of iron 3 chloride by using the balanced chemical equation. Right, so 2 moles of one to 2 moles of the other. And then what's the final step that we need to do then? We need to get into grams of iron 3 chloride. And we're going to use that by canceling moles on the bottom and going into the grams, the molar mass of it, on top. And we should find this to be right around 649. Yeah, so they had 648.62. So rounding, you get there. Yeah. And 10. Okay, so let's try another one. We're going to walk through it step by step, and we'll see how this goes. All right, so we have a very simple process. We're making water. This is what our grandparents did. And this is why we had the lakes and the oceans and stuff. They were actually assembling water, atom by atom. Water factories. Water factories, yeah, exactly right. Right? Sweatshops making water. All right, so we have 13 grams of hydrogen gas. We have 80 grams of oxygen gas. And we're asked which is the limiting reactant. Which one's going to limit this process? Will it be hydrogen or oxygen? All right, so first, get each value into moles, and so we can compare them. It's L, don't worry. All right, so we have 13 grams of hydrogen gas, 80 grams of oxygen. We're going to divide by their molar masses. Remember, hydrogen gas is H2, so it has a molar mass of 2 grams per mole. 2 grams per mole. So we run that through, and then we find that we have 6.5 moles of hydrogen gas. That's what we have in hydrogen. All right, so we're going to compare that then to what we have in the moles of oxygen. Oxygen is O2, so it's 32 grams per mole, 16 times 2. We're going to divide that in. We're going to solve for the number of moles of oxygen. All right, this one comes out to be 2.5 moles of oxygen. That's what we have. There might be points in time where you could look at what you have and look at the process and know, I know right away which one's limiting, because I know we're going to run out of this one much more quickly than the other. In times like this, though, it's kind of close. It's kind of close, so maybe we go ahead and follow through our method, divide each one by the coefficient from the equation. So hydrogen divided by 2, and oxygen moles divided by 1, and it comes out to be 3.25 to 2.5. So which one is our limiting? Oxygen. Yep, absolutely. So now that I know what is going to limit and shut down my reaction once it's used up, I can then answer like another question about this, like how many grams of water would be formed? Because I know when I run out of oxygen, I'm done. So what am I going to use here? Well, I need to go from moles of oxygen to grams of water. So because I've already done the math, I already know how many moles of oxygen that I actually have. I'm going to start with that. 2.5 moles of oxygen. I'm going to start with that. Now, how do I convert from moles of oxygen to moles of water? I use the molar ratio from the balanced chemical equation. So what is the ratio of oxygen to water? So it's a 2 to 1, or for every 1 mole of oxygen, we'll have 2 moles of water. So moles of oxygen have to be on the bottom because we want that unit to cancel. Moles of water on top. And then finally, we need to get into grams of water. Molar mass of water is 18 grams per mole. So moles of water cancels on the bottom, left with grams of water on top. And how many grams of water did we make here? Yeah, right around 90 grams of water. All right, now, does that method, does that walking through that kind of help you see what the process of steps that you need to do? no matter what the limiting reaction question might be, the same method can be applied, and you can reach the conclusion, or reach a solution to what you might make, or what you might use, or whatever. Okay, so we can follow this up with another question. So the same process. How many grams of oxygen are left over? Oxygen was the limiting reactant. So 0, because it's all used up. Haha. If I got you calculating really quick. Haha. How many grams of hydrogen gas though are left over? Well, remember, we're going to know exactly how much hydrogen we've actually used, and we know how much we started with. So we simply need to figure out the difference. Right? We can calculate how much we will use based on the using the limiting reactant as our starting point. Right, hopefully you've at least got as far as determining the moles of iron and moles of bromine that are present or that you have. Then the next step is to divide by, again, the respective coefficients from the balanced chemical equation. In doing so, we find that it's the bromine that's going to be the limiting reactant. Right, it's pretty close in this one. This one would be definitely one that you would need to take the time to run the calculations to make sure that you choose the correct limiting reactant. All right, so then the follow-up question is asking us how many grams of iron 3 bromide are formed. So we're going to start with what we have in moles, right? And we're going to get to, hopefully, iron 3 bromide in grams. Since we've already done this calculation, since we already know that's 4.31 moles of bromine, then we're going to start with that.
What's for rotary tomorrow?
Tomorrow?
Yeah, but I couldn't.
That you won't be here anymore.
Awesome. I don't know if she was the one that gave me like college slip, college visitation slip. Like asked me what day. I'm like Friday. Oh.
All right. So we'll start with the 4.31. Now, if you could start with the 96.5 liters of the liquid. You could do that, it's gas bromine. We could start with that, but since we've already done the work, we might as well just start with the moles. Okay. So one thing to caution you about: sometimes students will confuse these two values, and they'll actually work with the comparative ratios. Try to remember that you use these only to find the limiting reactant. You don't work with these numbers anywhere else. All right. Sometimes students will want to use this 1.44, and that's not going to get you anywhere. You need to go back to the amount that you actually have to work with. Okay. So it's going to be a two-step conversion. We have to go from moles of bromine into moles of the iron 3 bromide. And then finally, the molar mass of iron 3 bromide, which is 295.5. We cancel 1 mole of it for every gram of the iron 3 bromide. And now it's a matter of punching it through our calculator. So we should find that we have about 849 grams of iron 3 bromide that's formed. Right, and then there's one other question they may ask us in a question that's set up like this. And that's going to be how much of the excess reactant is actually remaining? Like how much of the other reactant is left over after everything's all done? If the ratio between the two reactants you're considering is the same, like if it's 2 to 2 or 1 to 1 or 3 to 3, then you know for every so many moles of one, you're going to use the same amount of the other. And you can go right from there. Subtract the difference, that's going to be the moles left, and then go to grams if you need to. But because they are not used at the same rate, you have to use that as a conversion fact. So you might as well just go ahead and set them up like you would normally. All right, so we're going to go into grams of the excess reactant being left over. So that's going to be bromine to solid iron in grams. We're using 4.31 moles of bromine gas. The ratio to convert it into moles of iron is 3 moles of bromine to 2 moles of iron. And now that we're in moles of iron, we can now convert from moles into grams of it using its molar mass, so 55.8. Now, this calculation will tell us how much iron has been used up. Right, so we've used 160 grams of iron to do this process to completely use up all the bromine. We started with 181 grams. We used 160, so the difference is we have 21 grams left over. All right, if we were given, I guess, a word setup like this, where we have molten sodium with solid aluminum oxide, and we're producing solid aluminum and solid sodium oxide, then we would want to obviously move this from the word equation to the balanced chemical equation. All right, so if we make note of that, aluminum is a 3+ cation, oxide is a 2- anion. That means we have Al2O3. Solid aluminum is just aluminum. I don't know why I put L after it. Oops. It's supposed to be molten aluminum. I don't know. I have to go back and review the process. This is how we refine aluminum, how we get aluminum from bauxite. But then solid aluminum oxide, we have an Na with a 1+ charge, oxide with 2 negatives, so Na2O. So we should have no problem with developing these chemical formula. Now we got to balance this thing. This one's not too difficult. We'll plop a 1 in front of the Al2O3. That means that we need to have 3 oxygens. So we can take care of that. And then that allows us to balance using the 6 sodiums and 2 aluminums to bring everything to balance. So we kind of, again, focused on the more complex molecule and then worked our way to more simple. So what we need to do is find the mass of aluminum produced. If we start with 575 grams of sodium and 357 grams of aluminum oxide. So right away we're thinking, crap, we got to figure out which one's the limiting reactant because it's really kind of hard to tell with the ratios we're presented with. So we go through the process all over again. We're going to divide sodium by its molar mass, and we're going to see how many moles of sodium that is. Right, and we have around 25 moles of sodium. For aluminum oxide, we're going to do the same thing. Aluminum oxide's molar mass is 102 grams per mole. So we divide that through, and we find that we have right around 3.5 moles of aluminum oxide. Now again, we look at this and we think, oh, well, this is rather easy. I mean, obviously we have a lot fewer moles of aluminum oxide than we do of sodium, so certainly aluminum is the limiting reactant, and it might very well be, but we still need to divide by the coefficient of each one respectively, and in doing so, we do confirm that it is in fact the aluminum oxide that is limiting. So we go ahead and we run this through our calculations. We want to determine the mass of aluminum that we'll actually produce if we start with these values. We have to use the limiting reactant to run this calculation. So we'll start with 3.5 moles of the aluminum oxide. And we're going to convert from moles of aluminum oxide to aluminum in a 1:2 ratio. And we will then convert from moles of aluminum to mass in grams by using the molar mass. Crunching the numbers, we find that this was going to make 189 grams of aluminum. Right, so we can term this as the theoretical yield. And again, it's if the reaction would run absolutely perfect. But we know that that's not the case. So suppose we run this reaction and we only get 172 grams of aluminum. Well, why might that be? It could be a number of things. One, maybe we couldn't just collect all the aluminum that was made. Maybe there's some aluminum left in our container. Maybe not all the sodium and aluminum oxide actually connected to form a reaction or cause a reaction. Maybe we oopsied and dumped some on the floor. Maybe something got spilled or lost. The percent yield. It's the actual amount that we obtain or measure that we have obtained versus or over the theoretical. So it's like anything, like practicing for and studying for a test, the number of points that you actually get versus the number of points that are available, number of shots taken versus the number of shots that actually went in. It's the same idea. The percent yield can never be greater than 100%. Right? If your percent yield is over 100%, something has happened. Something wrong has occurred. Maybe you overheated the hydrate or something. We did actually pretty good with our formula of a hydrate because none of the groups ended up going over 100%, which means we were pretty good about not overheating anything. So if we wanted to do percent yield on what we just worked with, we'd simply take the 172 over 189, and we'd find that it was 91% efficient, which is pretty good. A chemist in a refining plant would probably look at that and say, we can try to do better. What can we do about the process to make it more efficient? What about the process can we change to get more aluminum out of the process at the end? And that's really what a chemical engineer would focus on.